videotaping this for Adam. Okay, so anyway, we got a little bit of late start, Adam, but we're in chapter 10 of the book, and we're only a couple of pages into it. So we're talking about some of these concepts and the units of measure. And like I said before, if you take a further course in this, you know, which I won't teach, but if you take a further course in this, you might get into the use of these a little more. But for the purposes of this class, I just want you to know that electromotive force is measured in Gilberts, right there, GB. It's a unit of measurement in the centimeter gram second system for MMF. So if you have a coil with a length, a certain length, you multiply this constant 1.257 times the current, which is I, times the number of conductor turns, and you're going to get an answer in Gilberts. So they've done one down here. What's the total MMF for a circuit that has 4 amps of current flow and 200 conductor turns? You multiply the constant, and that constant is circumference to length ratio. That's a constant. It's mentioned in here somewhere, but right there. Constant of length to diameter ratio. So the constant times the amps times the length gives us a total force of 1005.6 Gilberts. Am I going to have you do any of those calculations? No. I want you to realize that Gilbert is the unit for measuring magnetomotive force. Reluctance is the next thing we talk about here, and there's a description and definition right there, is the property of an electric circuit that opposes the lines. So what is it like? Reluctance is the opposition to lines of magnetic force. So if you think about regular electricity, resistance or ohms is the resistance to current flow. So think about reluctance, the word right there, as a property that opposes magnetic lines of flux. And those are measured in an even more obscure term. I'll wait till you get that written down. Okay? So, remember we were talking about Maxwell's earlier. What is the reluctance in a circuit with 4.5 million Maxwells and a total circuit electromotive force of 2 Gilberts? So this is actually measured in, this is the term up here, rels. It's mentioned a couple times in there. But if we take the 2 Gilberts, we divide it by the 4.5 million Maxwells, we get this reluctance of that many rels. Sort of like the resistance to magnetic lines of flux. Okay?
Reluctance is rels?
Huh?
Reluctance is rels?
Reluctance is like resistance. It's in rels. Reluctance is in rels. The amount is in Maxwells. So the amount of magnetic lines of flux is in Maxwells. And then Gilbert's is the force that's in each one of those lines of flux. So we really don't need to get too deeply into that because it's not within the scope of this class. So there's some more calculations that you can do, which brings us up to permeability. And permeability, I think that's the next thing on your list, isn't it? Yep. So permeability, there's your definition right there. The ability of a material to carry magnetic lines of force. And it's abbreviated as a mu, which is the Greek letter M. And these have a unit right here of gauze. Now, gauze is an interesting and a useful thing. If I had my phone, I could show you an application, but if something like, if you're in a plant somewhere and they're having some problems with stuff going along in line or something that's happening, a lot of this equipment can become magnetized. It has an ability to absorb those magnetic lines of flux, and it kind of becomes a slow permanent magnet. And that can cause some interruption to electronic circuitry, or it can cause an interruption to a signal, a radio signal or something like that. So a good thing to have is a gauze meter. If you see right here, a gauze is equal to 1 line of force per square centimeter. Gauze, which is abbreviated capital G, measures the amount of density for magnetic lines of force. So you can take a gauze meter and you can walk up to an assembly line or a piece of equipment or a pipeline or something like that, a pipe that's carrying, and you can use that gauze meter to see how magnetic it is. A piece of equipment or a piece of metal, its ability to absorb and carry magnetic lines of flux is known as the permeability. And it's measured in gauze. So here's a simple little example that they've done here. The flux density is equal to the total magnetic lines of force in Maxwell's over the area. So if you have 1 Maxwell and the area of the object that you're measuring is 10 centimeters by 10 centimeters, you have 1 Maxwell over 100 centimeters, you have a flux density of 0.01 gauss. Now, how much is 1 gauss? Well, I can tell you this: if you have 2 gauss in something, usually these lines of magnetic flux are measured by Teslas. Tesla is the subunit to gauss. It's not mentioned in the book. Usually you have a meter that measures in microteslas, very small magnetic permeability. But I have seen, and I have pictures of, 16-pound sledgehammers that you can walk up to a pipe and it'll hold that 16-pound sledgehammer to it. It's not supposed to be magnetic, but it's built up so much magnetism by being under a power line or something like that, it induces that current into it, and it causes all of those domains to line up slowly over time and can become very magnetic. And in a lot of the work that I do, quite often we'll get out on a location somewhere and the welders will be working on a location and they'll holler at me or the boss or somebody and they'll say, "We can't weld this, it's too magnetic." So you go over there and they've got a file stuck to the side of the pipe, or they've got a hammer stuck to the side of the pipe. You've got to reduce that magnetism out of that material. If you don't reduce that magnetism out of it, you can't weld it. You're trying to weld it, and the hot metal jumping from the electrode to the pipe is flying off. It's like hot sand blasting coming off. It's so magnetic sometimes. So what you have to do is you have to go in and you have to wrap cables around the pipe in opposite directions, and you have to induce a current into that, and you have to flow. There's a formula that you can figure out for how many amps, how many turns, and how long, and that will reduce the gauss to 0. You have to get that gauss value right there down to 0 before you can weld it. Usually it has to be well below 1 gauss. You can probably get about 400 Tesla and still weld it. It takes 1,000 Tesla to make 1 gauss. But what I want you to know here, gauss right there is equal, and it's written as a capital G. That's the unit that we use to measure the lines of force for magnetism. And a material's ability to become magnetized is known as its permeability. measured in gauss. Does that make more sense? Really simple.
It's the measurement of those lines of force.
Yes, yes. So you have the magnetism of an object is its permeability, based upon its permeability, and that's measured in gauss. And the subunit to gauss is Tesla, interestingly enough.
Tesla's just a smaller indication.
Yes, yes. It takes 1,000 Tesla to make 1 gauss. And you can get the app. You can get an app on your phone that measures Teslas. Okay, so now let's look at this magnetization curve. We looked at this once before. We talked about the flux density, which is this, how much gauze there is. So as when you induce a current into something, and the current goes up, the magnetism of that material goes up until it reaches a point at which it's saturated. It can't take any more magnetism. Steel has a really high ability to absorb flux density. Iron is not quite so much, and then air is even lower. So when you have, if you recall in that one drawing that we had, in this drawing right here, where there's an air gap right here, this air gap can be useful.
So this is how much these materials can be magnetized.
Correct. We're still talking about the permeability of them. Air has a very low ability to be magnetized, extremely low. It's really not 1, it's 1.000004. But air is very low. And we put an air gap in some appliances like this to create a spark to go across there. For example, the heater that produces heat in your home or heat in your room, there's a furnace downstairs, and the gas comes on, the gas comes into the furnace, and then another switch tells the igniter to ignite. What happens, there's an air gap. And because there's an air gap, and there's a high voltage that's pushing that through one side of that, the cathode, then it jumps across through the air. Air has a lot of resistance to that flow. But it'll jump across, and that little spark that goes across here is what ignites the gas. So that can become very useful. But I want you to see that air has a really low ability to develop any magnetizing force. Steel, really high, really quick. Iron, a little bit slower. But if you notice, the maximum is about 600 or 6,000 gauss for iron, and it's about 15,000 for steel. We talked about that a little bit. Steel's a little bit softer. Okay, and then I think the next thing is hysteresis. Isn't it the next thing on the list?
Yes.
Okay, so here's our definition for it, right there once again. It's a property of those ferromagnetic. When I say ferromagnetic, do you understand that term?
Ferrous materials, iron,
Correct.
steel.
Good.
Durability.
Iron-based. So it's the property of ferromagnetic materials where the magnetic induction of a coil lags behind the magnetic field that's charging it. And I don't think we did a very good job of discussing this, so I thought I'd walk through this here. You look at this curve right here. You start at 0 right here in the center, okay? And as you increase the current that you're using on that electromagnet, as it increases, it goes up from 0 up this way to this point here. That's the saturation point. The saturation point can take no more magnetizing force. It's reached its maximum level of magnetizing force. on this particular chart here, at this point here, point they call it point A, it's at about 16,000 gauss.
So hysteresis is a relationship between flux and magnetizing force.
Correct. That's very good. Yeah. Some materials have a really good ability to be magnetized. You can't magnetize aluminum. There is another force that we're going to be talking about very soon that, well, I doubt I'm going to get to show you. Maybe they'll let me go down there and videotape the thing in operation. But some things have a resistance, such a high reluctance, that we can use that phenomenon to our advantage, like aluminum. Aluminum has a real high reluctance. So when
What's the difference between flux and magnetizing force?
What's the difference between flux and magnetizing force? Nothing. Flux are the lines of magnetism. If you go back to those loop pictures, right there, these lines that are going around, this is a conductor, current in, current out. So we've made a coil, and these lines that are going around, those are known as magnetic lines of flux. So you can see in these coils over here in the right picture, we have these coils spread out, and these lines of flux they don't look very strong because they're stretched out. But if we put that coil close together, they kind of gang up, and they concentrate on each other and make these nice, strong lines of flux. They're known as lines of magnetic flux, and they're measured in.
Coils are close together.
Yeah, and they're measured in. You should remember that it's measured in Maxwell's or Weaver's. All right. And then let's take that hysteresis chart another step. Okay, so as we induce that current in there, and it goes up to this point here, and then we turn that off, the current drops at that rate right there. So at one point, the flux density or the gauss is going to be at 0. This is 0, 0, right there in the middle. So as it drops, it crosses that line, continues to crosses that line. Now you're into the negative side, and you have a negative repulsion in gauze as well. It's trying to get rid of all of its lines of flux. Okay, but it lags behind. Notice it lags behind on the chart its ability. If you start it back up again, it's going to go right back up to there. Notice that there's this distance. I mean, this material, this area that's inside of that graph right there, is the lag area. You induce current into an electromagnet, and it takes a second to ramp up to full saturation. And then when you turn the power off, it has a tendency to lag behind and slowly give up its magnetism.
That's retentivity.
That's retentivity. Well, yes, that retentivity is a function of a material to resist giving up those lines of flux, which is another word we're coming up to here in a minute. So you can read this little paragraph right here and it'll explain all that, but what we're really looking at here is we're looking at the lag time in magnetization of the core behind the value of the magnetizing force, which is in Maxwell's, by molecular agitation. So it's really at the molecular level. Remember, we talked about magnets. First of all, magnets are made up of domains. A good strong magnet has domains that are lined up north and south. It's just a bunch of little magnets lined up. We take a bunch of magnets, we put them in line, the magnetic thing is stronger. And when we turn that off, there is a bit of lag in time, in seconds, before it is completely demagnetized, and then actually goes into a negative. Right down here it says, let's see, as magnetizing force is decreased to 0, the core material does not demagnetize at the same rate. Makes sense, right? You energize it, it ramps up. You demagnetize it, it ramps down. But it takes it a little bit of time and it lags behind it. That's what hysteresis is. It's the property of the material where the magnetic induction of a coil lags the magnetic field that is charging the coil. So it's behind the electrification of that coil. And when you shut it off, there is a little bit of lag before it's completely demagnetized. That's kind of the simplest terms.
So is it the same as retentivity then?
Retentivity is a function of it. Different materials have different rates of lag.
So hysteresis isn't a relationship between flux density and magnetizing force. It's the lag off of that.
Yes, correct. Correct. It's the phenomenon that is the property of materials and their rates at which they magnetize and demagnetize. And this is just a sort of a generic curve that we're looking at here. And this is a good explanation of it. I'm more of a graphics kind of a guy. I look at a graph and understand it better than I do the text. But if you follow this, it starts at 0, goes up to point A, point B, point C, point D, point E, point F, and back to A. It's the lag time in becoming electrified and not being electrified. Now, hold that in your mind, and then let's look at these. We talked about these yesterday, but annealed steel, the softer steel, notice the hysteresis curve. It's skinnier. So when we start here at 0, 0, and we go up to here, to point A, it only goes up to about 12,000 Gauss. But then when you turn the power off, it comes back to 0, and then all the way back down to the negative repulsion part of it. And the retentivity is a function of how big this is. Okay. So comes back down, re-energizes, comes back off, re-energizes, comes back off, re-energizes. That make sense? Okay. So notice that the graph for the hysteresis of annealed steel is slightly different than the hysteresis chart for hardened steel. So this is something that you have to keep in your head. If you're trying to make something that you want a small hysteresis curve, something that can really be magnetized quick and then give off its magnetism, you would probably want to look at annealed steel rather than hardened steel because the hysteresis chart is smaller.
Are all softer materials like that?
No, not necessarily. But most of these magnets are made out of some ferromagnetic material. When you're looking at some of the superconductors, the hysteresis chart on a superconductor almost doesn't exist. Instantly magnetized, and they stay magnetized. Something like neodymium, which you're familiar with. I actually have some sitting on my desk. I usually bring to this class. This is another hysteresis chart. Notice this is for magnesium, manganese, or iron. They have a rectangular hysteresis curve. So you're starting at 0 here. You take it up to here first, and then if you turn the power off, it goes backwards this way and then drops rapidly. And then when you re-energize it, it comes back up this way to that point, to the saturation point. This is the saturation point. This is the opposite of the saturation point. So here is, you were talking about retentivity. Retentivity is the ability of the core material to retain its magnetism after the magnetizing force is removed. You see the word retain in there. So just think of retaining its magnetism. Some materials have high retentivity. They really hold on to their magnetic flux lines, and they reluctantly give them up. And then others are rather quick in their characteristic. They have low retentivity. They don't hold on to it at all. You shut it off and it goes right down. We're talking about seconds here anyway, or microseconds. So yeah, this is just a comparison of two materials and their hysteresis charts, which shows a demonstration of how quickly they become energized and how slowly they become de-energized, and how quickly they can become re-energized and how quickly they give up their magnetism. Can you think of a place where this might be important? Like you want something to be magnetized, but then you want it to go off really quick.
Well, like you were telling the scrap story last time in that one magnet, but that one you had to switch the polarity of it to throw stuff off.
Correct. Yeah.
So
that's one use. I was thinking specifically of something like a speaker, because sound is, they use those magnets to move those cones on a speaker. So if you have something that is really slow, has high retentivity, you're not going to get the subtle movements in those speakers that you need to get the right kind of sound. So you'd want something with a relatively low to non-existent hysteresis curve. On, off, on, off. I mean, it can do that over and over and over and over, millions of times before it wears out. So there's applications for both ways.
Built a speaker out of a cup once.
Yeah.
That wasn't the best sound.
Yeah. This class, one of the things that we've done to change this is we moved away from a lab box that they'd sold here for 25 years, and it had that cup speaker in it. And it's like, even when you make it, the sound that you could produce in it was so faint, most people couldn't even hear it. So I'm the kind of guy that's like, if I'm gonna build a speaker, I want to build a speaker where we can actually hear some noise coming.
Do it with a bucket or something.
Yeah. So that's one reason why we changed to this class. Okay. Reluctivity is the measurement of that's not really good. What was I looking for? Well, this is the measurement of reluctance. So reluctivity is just a term that we say when we're talking about the measurement of the amount of reluctance. And we've talked about reluctance, the inability or the ability of some material to become magnetic or not. Okay, and we had come to this part where we talked about this left-hand rule for generators, and we talked about, just really quickly, when we increase, we have a magnet like this, North Pole and South Pole, and we have 1 amp of power in this coil, then we get this much lines of force. We get these flux lines here. But if I increase that to 3 times that much, then you should have 3 times the amount of lines of force. So it's directly proportional to the amount of power that's being applied to it, upwards and downwards. So if you have a larger thing and you have too much lines of flux, you can cut this amperage feed down to this coil, and it will slow down the amount of lines of flux. We kind of talked about that a little bit last time. Which gets us to this next really useful thing, which is the angle at which a conductor cuts through a magnetic field. So here we have a north and a south pole, and we have some lines of flux here in this magnetic field, and we're passing a conductor. So if we move this conductor this way, back and forth this way, you're going to produce no volts, because you're not cutting through the lines of magnetic flux. But if we angle that a little bit, and it says at 30 degrees of angle, and we move that conductor this way, Now we're starting to cut those lines of flux, and we get about a half a volt in this particular magnet. If I increase that angle more, now we're at 45 degrees, we've increased to 0.7 volts. And I think you can see as you go down, as you increase that to 90 degrees or perpendicular to the lines of flux,
So it's best to go straight across.
that's where you're going to get the maximum amount of voltage. So you pass this conductor through these lines of flux, you end up with a volt at 90 degrees. In this particular case, that's a very simplified simplification of passing a conductor through lines of flux. And we actually have a thing in the lab that you do where you can actually use your voltmeter and you can pass this conductor paperclip through two magnets, and you can see that it's actually producing current. Just one of the cool things of nature. Did I put Lenz's law on that?
No.
Okay.
Do you want me to write it down?
No. Well, you probably should know Lenz's law is right here. The basic principle used to determine the direction of an induced current. I think we looked at that with the previous drawing.
The hand thing?
Wasn't it right there?
Yeah.
Yeah, there it is right there. So the left-hand rule for generators, it just basically tells you the direction of those lines of force that we're talking about. Okay, so that takes us into generators. And this is a very modern, very simplified, type of a generator. And you get into a place where welders are being used or generators are being used to turn other appliances. This is a very simple breakdown of what this generator will look like. It's broken down into, it's got a couple more things here on the next page, but the first thing we're looking at is the field windings. The field windings are right here, and really all they are they can be a big permanent magnet, or they can be an electrified coil, but they put them outside of the moving part of that and induce a current in there, and that magnetism is what pushes that motor and makes it start turning. So you electrify this, and this armature, which is this piece here that's resting on bearings on either end, very freely turns inside of those field windings, and as that turns, it creates little bits of voltage by passing that conductor through those lines of magnetic flux. If you notice on these on the armature, which is this piece right here, sometimes called the rotor, doesn't really say it here, but this is sometimes called the stator, this is sometimes called the rotor. The stator stays still and the rotor rolls. So that's how I remember that.
So armature, field windings, stator, rotor.
Yeah. Yeah. Notice you can kind of see a little bit of an angle to those. There's a slight little angle to them, the way those are put in there. A lot of them look very straight, but they have a slight little bit of an angle, and that's so those magnetic lines push that armature away from it. It pushes it in the direction that you want it to spin. And there's a certain number of these slots in the armature that have electrical wiring in them. They're wrapped around back and forth all the way through that to create this armature that as it spins, it breaks that magnetic field, and then that current is carried to the back part here, to the commutator. And on the back part of that commutator, we're getting away from these now, but they're still very, very popular. You have this part here, and you have a bunch of isolated little sections.
They go against the brushes and basically
Yes.
switch the current.
Correct. That's where the brushes are usually curved to roll on that, they actually touch, they come in contact to the commutator. And as that turns and breaks those magnetic lines of flux, it sends the voltage, it sends the current back to this part of that generator, known as the commutator, and then the brushes pick that up. And then it's carried away to whatever we're going to use it for, whatever the particular use is. And I think the next picture shows, yeah, there's the commutator, and there's the conductors that come off of that commutator. So that's sort of the business workings of a generator. Very simple. This is an incredibly old picture of brushes. I mean, that is so old, you might still see it. I mean, I do a lot of work down in the Gadsby power plant. I don't know if you know where that's at. It's a big power plant in Salt Lake City. You go down there by the state fairgrounds, or you go like I-80 going out to the west, you go right past Gadsby. It's the one with the 3 great big smokestacks. And they have a lot of old equipment that's like this. If we were to go into the Pioneer Station and got to look inside there, you would see brushes that look like this. But we're getting away from these, and there's much more modern, better technology for this part of the generator that picks up this circuit. Interestingly enough, most of this is DC generators. So they have a real problem with friction, so they have to make sure that the bearings and all of those pickups have very little resistance to the turning of that by the wind. Wouldn't be very hard to stop it at all. Okay, so we get this set up now. Have a nice magnet here. Have lines of magnetic flux going back and forth. We have one conductor, and they have made a red side and a white side for you, and they've set up a sine wave over here for you to see how this is produced. When this is turned, so we bring power from somewhere, and we turn this, then it pushes this commutator, this conductor, the conductor, through these lines of flux. So now notice here, the red one is up at the top. Now we've gone 180 degrees, so now the red one's at the bottom. So we've made 1/2 of a turn, and notice that it's produced 1/2 of the sine wave. And then the bottom one, now the red is back at the top, and we have produced 2 lobes of DC positive power. Only. So in one complete revolution of that conductor through those lines of force, we have produced 2 little spitzels of energy here of whatever value they just arbitrarily put this at. We have produced a little bit of power that goes to this external power source. So that's a single phase. That's just one phase. So what if we add 3 phases? What if we add another lobe to it, another conductor to it? So now you have this conductor here, and you have this conductor here, both on the same armature, and they're turning at the same time through these lines of magnetic flux. And as they turn, each time that one red loop goes past and cuts through at 90 degrees, goes through that lines of flux, it produces this kind of power production. So it's hitting 2 times instead of 1. Instead of it being just one lobe and then another lobe, now you got 2 of them. You got 1, 2, 1, 2, 1, 2, and so on. Doesn't really end there, because we could actually put more conductors in there to turn through there, and we could actually end up with 3-phase. With 3-phase, you have even less distance between these maximum outputs on this sine wave, so there's less space in here where whatever appliance is being used sees that drop in voltage. It will see it much less as we stay in this area right here all the way across with another commutator ring there.
Could you just put more wires in to make it smoother?
Yep. Up to a point. And that's it. That's it for that chapter. I don't want you to get bogged down in the calculation of, figuring out how many Gilberts there are in a particular thing, or how many rels there are, that sort of thing. I want you to know reluctance, retentivity, permeability, the things that I have listed on that sheet right there, and possibly the unit that you measure them in. But it's unclear because there's so many of them. If you're dealing with a large amount of lines of magnetic flux, then you're going to be using something like Weber's per, it's Maxwell's per Gilbert, and Weber's per amount of unit, amperage unit. So I don't know necessarily that you need to know that. It's not really necessary for this class. It's necessary that you know what those terms mean and what the units of measurement for them are. And I think that's really all we're going to know. And Adam, if you're listening to this, I'll put, you don't have one of these sheets because you're not here. I will put this sheet on Canvas for you, so you'll be able to access this. This is out of chapter 10 of the book, so hopefully I haven't left any men on base. You got any questions? So many questions, right?
So you go back to magnetic flux, get that. Electromagnetism, gotta find a good definition for that.
Electromagnetism?
The relationship between magnetism and electricity produces electricity and creates magnetism. Something like that.
Just remember, we take a conductor and we electrify that conductor. Just by electrifying that conductor, it sets up lines of magnetic flux around it. So if we loop that conductor, then we create loops of magnetic force in that loop that can be, we can put more loops together and strengthen that field of force, and we can make a really strong electromagnetic magnet of some kind. And then that can be used in generation, it can be used in locomotion. We can use that same thing in a motor. That's what we do in a motor. We put two magnets opposite of each other and we energize them in such a way that they repel each other. If you remember that first slide that we looked at where it had conductors that were, where the power was going in the same direction, they were parallel and they were repelling each other. And then the other one you had the conductors where the power was going in opposite directions and they attracted each other. So we use that phenomenon to make motors and to make generators and to make solenoids and to make all kinds of things. That very simple basic idea of electromagnetism, which is simply a current going through a conductor. We bend that conductor in certain ways that gives us a geometry where we can use the force of those electromotive forces because they're strong. They're quite strong. We can use them for a lot of different uses in industry and in production and manufacturing. We use them to create welders. We use them to create, large generation plants, things like that. We use that same phenomenon of electromagnetism to do a lot of work for us. So, if you were to go from here and get into the R&D, research and development of newer and better ways of using this force, then you would need to know all of these calculations. But for our class, you need to know the phenomenon that creates the electromotive force, that creates electromagnets, and mostly the nomenclature, what it is, and maybe the units that we measure them in. But you won't use them much beyond this class, even out in an environment where you're working as an engineer. You really won't use those things. Those are things used by people that develop the theories and the concepts that creates the equipment that we purchase and put into a manufacturing situation. Quite often we don't repair those sort of things. You can repair them, but it generally takes a very highly trained technician to do it. Usually has to be brought in to fix things.
How do you actually go about designing equipment, like the wood equipment you designed in the dog food line? Is there software that you use for that? How do you go about doing that?
It'll make you laugh, but most of my design was done on cocktail napkins and placemats at restaurants. And then sometimes in my motel room or at home, if I was here, I would sit down with quadriline paper and I would flesh out my concepts. And then I would take them to the engineers. We had a whole, group of engineers, and it was their job to draw the stuff out. So I would bring my concepts to them, and they would do it. And then they would kick back to me a set of working prints. They would crunch the numbers and they would do the dimensions. And often I would
Classical engineers. Classical engineers.
Yeah, classical engineers. And they were the ones that would call me and say, this dimension or that dimension, or, have you taken into account this weight, or have you taken into account how much power is going to be needed to do this? And I would usually have to know, well, a 15 horsepower motor should develop enough torque to do this. But oftentimes they'd come back and say, calculations were too low, it's going to take a 20 horsepower motor to do it. I said, oh, okay. So if I put a 20 horsepower, can I widen the bed of this thing any? No. 20 horsepower is going to get what you've drawn here. So if I needed more bed, I'd have to get a bigger motor. Yes. Well, do you have is there a chart or something I can look at? It's like, no. Just how big do you want to make this? Because that adds more weight to the bed, and there was resistance, so you have to have a bigger motor. So I would conceptualize most everything, and then kick it to them, let them do the drawings, let them do the calculations, and then we worked really well back and forth to come to a final solution. But there was a lot of times I was kind of on my own. I had engineers in Phoenix and I had engineers in Ogden. And there's plants in Portland, there's plants in Seattle, there's plants in Montana, there's plants in Ohio. And those two engineering departments took care of all of the engineering for the plant. For example, we went to Ohio, and Jack had bought a dog food plant there, and he wanted to put a dog biscuit line in the Ogden plant. So we went there, took a bunch of measurements, and then began disassembling this biscuit oven, which is about as long as a football field and probably about as wide as these desks are and twice as high. So we had to take that all apart, put it on trucks, and then we had to come back here to Ogden, and we had to design the building to put this in. The building didn't even exist yet. So we're going to need X amount of power to run this building, because you're going to have 2 lines of dog food, dog biscuits, plus the mixers, plus all of the conveyors and everything to bring it to the mixers. So that's the kind of work that I had to do as kind of a field engineer. But I never wanted to sit in an office and draw. So most of my work was done on cocktail napkins, placemats at restaurants, and notebook paper. And then I would turn them over to the classical, I call them draftsmen, the people who draw the pictures for me. So a lot of times I just kind of knew by rule of thumb what I was going to have in power. So it comes to you over time. So any questions, any more further questions on that? Friday, we're gonna meet at 1 o'clock up at the power station. So Adam, if you're listening, 1 o'clock substation where we were last Friday. He's gonna take us into that substation and then down here to the Tracy Science Building. Show us a little bit more distribution. Okay?
Okay.
That's all I got to say about that there. Unless you have questions.
How long does it take to learn all those rules of thumb?
A long time. It takes a while. Depends on you. Depends on how quick you pick things up. I think I had a tendency to be kind of, I don't know, sort of a rogue. And I would try things thinking that, you know, I keep thinking about electrical motors, you know, thinking that a 5 horsepower motor would do this. And then I would build the things, get it all built, and then find out that, yeah, 5 horsepower motor makes everything work. But then as soon as you put product on it, oh, I didn't even think about putting product on it. So that 5 horsepower motor just stalls. So those really expensive kinds of, I guess I'd call them errors. You know, it's kind of like Edison. Edison never really invented the bulb. It was actually Westinghouse that did. But Edison went through, I think it was 1,000 different tries. And when somebody asked him about, you know, are you disappointed that you had 1,000 mistakes? And he said, no, those weren't mistakes. Those were 1,000 steps to getting to the one that did work. And that's kind of how you gain the experience.
Found 1,000 ways to not make a light bulb.
That's it.
Yeah.
Yeah. And I think though that it was Tesla through Westinghouse that actually came up with the first incandescent. So, but even that's not in vogue anymore. The incandescent bulb's not. We don't use them. We use LEDs.
But without the incandescent bulb, we probably wouldn't have LEDs.
Probably true. It's all a step. It's all a learning curve. I called it tuition. You know, some of those really hard, expensive tuitions, you do not forget. You learn from the mistake. You really do. And after a few years, 7 to 10 years, you become a little bit sharper. And you remember that one guy that you met in Smithfield that had a real knack for, you know, switchgear, or had a real knack for conveyors, or had a real knack for structure, something like that. And you develop this library of people that you can consult. And that takes time as well. And unfortunately, a lot of people refuse to give up information because information has been seen as power for so long. So sometimes you just have to learn it on your own. The first rockets that von Braun and his guys produced were utter failures. But by the time they had the first V1 or V2, von Braun was seen as the mind, the genius behind rocketry. And you and I might think, well, that's kind of a simple thing. You put a fire on the bottom of something and you shoot it in the air. Yeah, but how do you keep it? How do you keep it stable? How do you guide it? There's all kinds of problems that you have to overcome. And that's the same way with having a career in engineering. You'll start out hopefully in a place where you have a lot of people that can, you know, guide you as a mentor. And you have to have the experiences. Everything is not going to come to you. I remember when I first started working at Hercules, which was a rocket plant, by the way. I was so scared. I was 24 years old, something like that. New family, a couple of babies. And I was so scared when I started out there. I thought, they're going to ask me something I'm not going to know the answer, and they're going to fire me because I don't know the answer to something. But I found out that most of those guys were just doing the same thing I was doing. They were just trying to figure it out as they went too. And it was a real eye-opener for me, because I found out that the way I had been taught in my household from my parents was, you have to know everything, and if you don't know everything, then you're stupid. Well, I found out that's not true at all. And I found that I was under the tutelage of some really old guys that had skinned their knuckles and had lots of failures, and they were able to tell me, no, wait a minute, no, John, don't do that, because if you do that, then this will happen. What we have to do is we have to do this. And then that's kind of the way I learned. So several years at Hercules helped me to become a better broad spectrum engineer. I learned how to use the lathes. I was a good welder already. I learned electricity out there. Made a fool of myself many times. I went running. I saw my friend down at the end of the big building, and he had pulled a piece of equipment in there, and he was going to clean it. And so he was out there spraying with this hot water thing, and the steam and the vapors were just rising up into the air. And as I was pushing my tool cart, I looked back at him spraying that thing down, and I saw the steam and the vapor going up towards the ceiling. And there, in those old buildings, there was 3 uninsulated wires, 440 3-phase, on the wall. And I thought, oh no, he was right underneath them. I thought, he's gonna kill himself, because those water vapors, the steam will contact the wires, and then it'll shock him. So I went running down to the building. Yeah, stop. I think his name was Roger. Roger, stop. I went running down through the building, and everybody was following me. And I ran over there and I said, stop, you're gonna electrocute yourself. And he kind of looked at me, went back to spraying. I was like, stop. He goes, what are you talking about? He says, I said, that steam is it's gonna contact those 440 3-phase power lines up there, and it's gonna like electrocute you. And he goes, water doesn't conduct electricity. Pure water doesn't conduct electricity. Steam is pure water. And there's no way that could shock me. So everybody was laughing at me, because I guess I was the only one that didn't know. And I learned my lesson, that pure water is one of the best insulators there is. It's the stuff that's in the water that conducts electricity. So when you have something as hot as steam has nothing but H2O in it. So it doesn't conduct electricity. So I made a lot of mistakes like that. And I had a lot of older guys. There were a lot of older gentlemen. I thought they were ancient old. They're my age. They were my age now, and I was just a young guy like you. And they just kind of laughed at me, and they put their arm around me, and they said, just stick with it. Don't get discouraged because of that. That's how we learn. That's the tuition of life that you have to pay. But you don't forget those things. So you add those one thing on top of another as you go through life. You learn stuff. And like I tell everybody, I tell all you students, make your education your own. Learn the stuff that is really interesting to you. Hold on to that stuff and utilize it, but follow what really interests you. And don't let anybody dissuade you from that. So that's kind of what I did. And I put myself through college doing that, put myself through university and 2 master's degrees doing kind of what I thought was an interesting occupation. So now I'm getting too old to do that stuff. Can't do it anymore. Well, I have a online conference at 2 o'clock, so.
Thanks for your time today, John.
Oh, my pleasure. I'll see you up there on Friday.
Yep.
And we'll have a good old time. I'll have a question sheet for you to carry with you, and you can
Question, but you just take the belt street that goes around the university up
Yes.
there, right?
Yep.
Okay.
I don't think there's a path that comes up, a walking path. I don't think there's a walking path that goes up to it. You just have to go this street right out here, up around behind, and it's right up the top. You just keep looking up, you'll see it.
1 o'clock, right?
1 o'clock. If you need me, pick you up, call me or text me or something.
Should I stop this recording?
Oh, please.